So hi guys, welcome to my channel. So today I'll be solving this problem, which is topological sort. So let's read the problem. Difficulty is marked as medium. So given an adjacency list for a directed acyclic graph where adjacency list I contains a list of all vertices j, and there is a directed edge from vertex I to j with vertex v vertices and e edges, and your task is to find the topological sort. Okay, so for every directed edge u to v, u must come before v. Like this is the definition of topological sort given. So let's try to see like how we can solve this. By the way, there are two ways to solve this topological sort: DFS and BFS. DFS I have already solved and uploaded. Now it's turn to solve BFS. So what is topological sort? Okay, so we are given this particular graph. Let me change this. We are given this particular graph and we have to find the topological sort. Whenever sorting comes to our mind, means there is something following a specific order. So we have to sort the graph in a topological manner. Okay, so let's write what is the topological sort for this. So it's given that for every directed edge u to v, u must be coming before v in ordering. Like if there is an edge between u and v, so whenever we write a topological sort, let's say u comma v, means u is always coming before v. So in this manner we have to find the topological sort. So in this case it will be 1, then 2, then 3, then 4. You all can check that 3 is coming before 4, and here also 3 is coming before 4, and 3 is after like 1, and here 3 is after 1. Okay, so let's see another graph. Okay, so in this what we are given is 1, 2, 3, 4 and 5. So there is the topological sort will be 1, 2, 3, 4 and then 5. But here is the like catch. We can also write the topological sort as 1, 2, 4, 3 and 5. Okay, how? Why? Because you can see that this is also a valid topological sort and this is also a valid topological sort. Why? Okay, 3 is coming before 5. Here 3 is coming before 5. Okay, 2 is coming before 5. 2 is coming before 5. Okay, 4 is coming before 5. 4 is coming before 5. Okay, 1 is coming before 3. 1 is coming before 3. Now let's see this one. 4 is coming before 5. 4 is coming before 5. 3 is coming before 5. 3 is also coming before 5. 2 is coming before 3. 2 is coming before 3. 2 is coming before 4 and 2 is coming before 4. 1 is coming before 4 and 1 is coming before 4. So no matter what are the nodes you are given, okay, I'm talking about this one. No matter what are the nodes you are given in a particular level, you can write it in any order. Like I have done this. Okay, 4 3 or 3 4, because it doesn't matter that you have to visit this and then this, or visit 4 and then 3. You can write it in any order until and unless the one thing should be followed is the previous node should be visited first, then only you will be visiting this, and after visiting all the nodes, then only you can visit to next level, like level wise. Okay, we have visited 1, we have visited 2, we have visited 3 4, then we are visiting 5. 1 2 then 3 4 in a single, and then 5. Okay, so I hope the topological sort is clear. And one more thing about topological sort is this algorithm is also known as Kahn's algorithm. Kahns, Kahn's algorithm. So we'll be using this approach, topological sort, like Kahn's algorithm, to detect that whether this cycle is present in a directed graph or not. So I'll be uploading this very soon. Okay, so now why topological sort can be only calculated in directed acyclic graph? So tell me one thing. There is a node given 1, 2. Okay, there is no directed edge. Okay, undirected edge. So why we can't able to calculate the topological sort? So in this we are not able to identify that which node is coming first. So let's say we have written 1 and 2. Okay, we are looking from this side, then we can see that 1 is coming first, then 2 is. But if we look from this side, okay, then 2 will be coming first, then 1. So what we should consider? So if the graph does not contain the directed edge, so it is not possible to find the topological sort. Okay, now tell me another thing, like directed is clear. Now why acyclic? Okay, this, let me make this directed also. If directed also given, but it is cyclic. Okay, you all can see that there is a cycle in this. So why can't we able to find this the topological sort in this? Okay, let me write this. We have written 1. Okay, 1 is visited first, then 2. Okay, I've written 2, then 2 is visited first, then 3, because there is a directed, then 3. But 3 is visited first, then 1. 3 is visited first, then 1. Okay, 1 is visited first, then 2. Okay, 2. So this will be going as long as like infinity, because we don't know which node should be coming first, because there is a cycle. So in cyclic graph, topological sort is also not possible. So I hope this is clear, that why the topological sort is only possible in directed acyclic graph, means DAG. We call it as short form as DAG. Okay, so now let's see how we can solve this problem. Okay, so I have taken this example, this second test case, and we'll be dry running the code, like what is the approach to solve this problem using breadth first search. And after that, we'll be matching that whether we have calculated the like correct like topological sort or not. So what we'll be doing, we'll be calculating the in degree of each and every node. Now what is in degree? In degree is nothing but number of edges coming towards that node. So in degree of 0 is 2, in degree of 5 is 0, in degree of 4 is 2, in degree of 1 is 1, 3 is 2, 2 is 1. Okay, so what we'll be doing is we'll be adding all the elements inside the queue, okay, whose in degree is 0, because here we can see that first element of every topological sort is the one whose in degree is 0, because here in 1 there is no edges coming. So in degree 0 we have put first element as 1. Okay, so here also whose in degree is 0 will be putting okay, how it's 2, it should be 0, because in 4 there is no edges coming towards 4. Okay, so I'll be pushing 5 inside it, then 4 in Q. Okay, okay, now I'll be making the in degree vector. Okay, so we'll be iterating the in degree vector and pushing all the elements inside the queue whose in degree is 0. So let's say 4 is 0, 5 is 0. So we have pushed 5 or 4, no matter, you can put 4 first and 5 first. It's like depends on you. Now let's iterate. Like I have taken out 5 and removed 5. Now if I remove the edges, I will see in the adjacency list what are all the elements we can visit from 5. So it is 0 and, let me change this, it is 0 and 2. So if I remove 5 and 5, then these two edges will be removed, and the in degree of 0 will be reducing it to 1, because this edge is removed from 0, this edge is removed from 2, so we'll be reducing it. Okay, so 2's edge will be reduced to 0 and 0 edge will be reduced to 1. Okay, so now what we'll be doing is whatever nodes we have reduced will be checked that if it becomes 0, okay, 2 becomes 0, so we'll be pushing it to our queue, will be pushing 2. Okay, done. Now again taking all the elements from the queue, which is 4. Okay, so now we can see that, let's reduce to 1, let's reduce to 0. This we have already covered. Now exploring the 4, what are the nodes we can visit from 4? It is 0 and 1. What if we remove the edges from 4? This we have removed, this we have removed, so in degree will become 0, and this in degree will become 0, because if we remove all the edges which is coming towards 0, this is already removed, this is already removed, so there is no edges coming towards 0, so the in degree is 0. Now here also there is no edges coming towards 1, so in degree is 0, both are 0. So what we'll be doing, we'll be reducing this in degree of 0 to like it was 1, we'll be reducing it to 0. Now it also reduced to 0, so 0 we have reduced to 0. Now we'll be pushing 1. Okay, now what we'll be doing, we have explored the 4, we will be exploring 2. So now what are the nodes we can visit from 2? We can visit 3. Now what if we remove all the edges that is coming from 2? Then the 3 in degree will reduce to 1. Okay, will be reduced to 1. Now the work of 2 is over. We'll be checking that whatever elements we have reduced, whether it is reduced to 0. No, then you are ready to go. Now we'll be exploring 0. What are the nodes we can visit from 0? We'll be checking in the adjacency list. There is no nodes we can visit. So just remove this. Now it comes to 1. What are the nodes we can visit from 1? We can visit to 3. You can see that we can visit 3 from 1. So we'll be reducing this in degree to 0. So finally we'll be reducing it to 0, and it will be reduced to 0 and pushing it in the queue. Okay, this has covered. Now we'll be covering the 3. Now what are the nodes we can visit from 3? There is no node, so we have done. Okay, I forgot to write all the elements in the sequence while we are visiting. So it was like the same order in which we have visited in queue. So it is 5, 4, 2, 0, 1, and then 3. And magically you can see that we have find the topological sort. Okay, so now validate the whatever topological sort we have found. Okay, so let's take and pick one by one edges. So 2 is coming before 3. Let's check. 2 is coming before 3. Now 5 is coming before 2. 5 is coming before 2. Valid. 5 is coming before 0. This edge. So 5 is coming before 0. Let's check. 5 is coming before 0. Valid. 4 is coming before 0. 4 is coming before 0. Valid. 4 is coming before 1. 4 is coming before 1. Valid. 1 is coming before 3. 1 is coming before 3. Valid. And 2 is coming before 3. Here you can see that 2 will be coming first, then we'll be visiting 3. So 2 will be coming first, then we'll be visiting 3. So this is the valid topological sort that we have found. So this is how the approach is working, and let's directly jump into the code. So what I have done here is I have initialized the in degree vector like this one in degree. So here what we are doing is we are calculating the in degree by iterating in the adjacency list. So we are calculating the in degree by seeing that what are the edges that is coming towards that node. Okay, we are doing this. Now we have initialized q, initialized vector answer. Now we'll be iterating in the in degree. Okay, we'll be iterating in the in degree and checking that if in degree of I is equal to 0 means we can directly put into the queue. Like in this case 4 and 5, whose in degree is 0, we have directly pushed 4 and 5 into the queue. Okay, now answer dot push back I, like 5 and 4 we have already explored, so we have already, this is the answer vector, by the way, this is the answer vector. Okay, so we have pushed 5 and then 4 in the answer vector. Now while not q dot empty, we will be taking out the elements one by one and exploring it. Now we'll be exploring the node which is in the front. We have explored 5, pop the elements, and then we'll be putting 5 in the adjacency list and asking that what are all the nodes we can visit from 5, give me. So it will give 0 and 2. Okay, we'll be reducing in degree of v, means v 0, first 0 will be coming. In degree of v minus means we'll be reducing one edge from 0, and then check that if in degree of 0 becomes 0, okay, like after reducing it, if it becomes 0, then what we'll be doing, push directly into the queue and push it into the our answer. Okay, push directly into the queue and pushing it in our answer, and finally returning our answer vector. So this is how the code is working. Let's run it and let's submit it. Okay, so this is how we are solving this problem, topological sort, and I hope the approach is clear and the code is also clear. So thank you for watching and having patience. So thank you.